Okay, so we've calculated discharge from a slug injection, but what if I did a constant rate injection? Can we use dilution gauging to our advantage in this case? Absolutely we can. Let's look at how on the next slide. So this is going to be with a process called end member mixing, with the idea that we have two inputs, the upstream flow from the river and the injection from our constant rate, pictured in orange, and those contribute to the concentration and the discharge that we observe at our upstream location shown in purple. Now I've drawn it here as sort of a river as I usually do. Let's just draw this as a schematic. So we've got from the upstream shown in black, Q and C with a subscript U for upstream. Our injection has a discharge and a concentration with a subscript I, and our observed well-mixed concentrations subscript O. And so what we're going to do is picture that those two inputs and one output can be related to one another. We'll draw a control volume to do an end member mixing analysis. And from this setup, we can write two conservation of mass laws, or two equations using conservation of mass. The first would be conservation of mass of water. Sometimes people just call this the continuity equation. The idea that the flow out of that box at steady state has to be equal to the sum of the flows in. In other words, Q upstream plus Q injection must equal the Q outflow. The second conservation law that we can write is conservation of mass for our tracer. And so for our solute tracer, the mass rates look something like this. How much mass is flowing in from upstream? Q upstream times C upstream. And the same for the injection, QI times CI. So the left-hand side represents the mass rates flowing into our control volume. The right-hand side, QO times CO, the mass rates flowing out of our control volume. So this represents a system of two equations with two unknowns. There's a smiley happy atom drawn on the right-hand side because I know it's a solvable problem. And I can actually use this to estimate QU, so the discharge at the upstream end of my study reach. Now, a couple of common simplifications that people will often make. If the injection flow is much less than the upstream flow, you might assume that QI is equal to 0 up in that conservation of water mass equation. And down below, if the concentration in the upstream end has no background, or if you've background corrected it, you might be able to assume that the concentration upstream is 0. Neither of those is perhaps strictly true, the first one being the more questionable, I think, especially if you're in a small stream with a fairly fast pumping rate. But they are simplifications that make the algebra just a little bit easier. If you're trying to work something out on the hood of a truck before a field experiment, those are an easy go-to to help make your life a little easier. So, with our end member mixing analysis, we've got a system of solvable equations. We can now estimate discharge at the upstream end of our study reach based on end member mixing. Importantly, this is again assuming that the observation point is close to the injection. So far enough downstream that things are well mixed, but close enough that you're not losing mass between the injection and observation points. So the same limitations we discussed in the previous video. Okay. Here, that's what I had for tonight, or for this lecture. I will see you on the next one. Thanks all.